Hello everyone, this is Rajiv Sanaki, Department of Civil Engineering, Jain Polytechnic, Belgavi. So in this lecture, we will be covering the second half of Unit 2, that is design of doubly reinforced beam. So the unit consists of two portions. First one is design of singly reinforced beam, and the second part which we will be dealing with today, that is doubly reinforced beam. So in the second half we have three lectures. Those are lecture 16, 17 and 18. So the content in these lectures are what is a doubly reinforced beam, and coming directly to the problems, that is design of doubly reinforced beam. So here we are designing only for shear, and there are problems on simply supported beam and cantilever beams. So what is a doubly reinforced beam? So in the previous lecture we discussed about singly reinforced beam. So the name itself specifies that singly and doubly means reinforcement. Singly means provided only on one side, doubly means reinforcement of steel which is provided on both the sides of the beam, that is in the tension as well as in the compression zone. So here you can see in the image or the picture a doubly reinforced beam where you can see stirrups as well as steel bars at the top as well as at the bottom, and here it is mentioned compression reinforcement and tension reinforcement and stirrups. Here one more view of doubly reinforced beam where bars are provided both the sides. Now coming to design of doubly reinforced beam. So before going to the problems, there is a procedure of design of doubly reinforced beam, and the problems are quite short compared to singly reinforced beam problems. So step 1, what we are doing is determining the limiting moment of resistance for a given cross section using equation of singly reinforced beam. So here you can see it is the equation to determine, or balance section means the equations, the two different equations where you can determine the limiting moment of resistance. Step 2, if factored moment, that is mu, is greater than mu Newton, then doubly reinforced beam is required to be designed for additional moment. That is mu minus mu limit is equal to FSC ASC D minus D dash. So FSC value we get from page number 70 of IS 456, and ASC, it is a value of area of steel in compression zone. Step 3, additional area of tension steel, that is AST2. AST2 is equal to ASC FSC by 0.47 FY. FSC, as I told, we get from IS 456 page 70. ASC we calculate, and FI is given, or we should assume it. So final, the total tension steel AST is equal to AST1 plus AST2. Design of doubly reinforced beam. So here there is a problem given. Determine the reinforcements required for a beam B is equal to 300 mm, D is equal to 600 mm, factored moment is equal to 320 kilonewton meter. Assume FCK and FY as 15 and 415. So in this problem, breadth is given and overall depth is given and factored moment is given. Now we have to calculate mu for concrete failure. So D is equal to capital D minus cover minus diameter of the bar divided by 2. So 600 at least is capital D minus 25 is the cover minus diameter of bar we are assuming, that is 25 divided by 2. So finally effective depth we get is 562.5 mm. Mu limiting is equal to 0.13 FCK BD square. So FCK BD values we know, substituting in the equation we get mu limiting, that is 196 kilonewton meter, which is lesser than the required, that is 320 kilonewton meter. Next step, we determine balanced steel required. So P is equal to 0.72%, that is percentage of steel. So AST1 is equal to 0.72 by 100 into 300 into 562.5. So AST we get is 1215 mm square. The next step, moment to be taken by steel beam. Mu2 is equal to mu minus mu L, that is 320 minus 196, we get 124 kilonewton meter. Step 4, calculate AST2 assuming tension, yield, steel yields. So here you can see the equation, AST2 is equal to mu2 by 0.87 Fi d minus d dash. In the design steps we had written this equation, so we are substituting the values in this equation. We get AST2 is equal to 654 mm square. So step 5, total tension steel AST is equal to 1215 plus 654, we get 1869 mm square. Step 6, stress in compression steel, d dash by d is equal to 37.5 by 562.5 is equal to 0.067. Now Fs is equal to 353 Newton per mm square, that is assumed from the code book. Step 7, so area of compression steel. So AST2 into 0.87 Fi by Fs. So Fs we are taken from the table. By substituting the values we get 669 mm square. Now after calculating it by actual IS456, the next method is by SP60, parameters used for use of tables. So d dash by d is equal to 0.07007 mu by bd square. So substituting in that equation we get 3.37. Now using tables we have d dash by d is equal to 0.1, percentage of steel is equal to 1.117%. So AST is equal to, substituting the values we get 1885 mm square. Thank you.